Welcome to Algorithms with Professor Caleb. Today I want to talk to you about the relationship between our theoretical analyses of the running time of our programs and the actual running time when we go to run them. So let's start with a bit of a review of algorithm analysis. From the code, we're going to determine the theoretical running time, where we're going to count either specific operations or steps. So operation examples are things like comparison or moves of data in things like searching and sorting. We're also interested in things like arithmetic operations in some cases. It can be lots of different things. Steps are basically a segment of our program that doesn't change its running time when we change the input. When we calculate our running time, we're going to base it on some input characteristic, which might be something like length of the input for something like sorting. It could also be the size of an input value. So if you're looking at the running time to calculate a factorial, that's going to be based on how big the number is that you're calculating the factorial of, because that determines the number of multiplications that you need to do. And then, of course, we typically will put that analysis into a special notation. We often use big O, which is the most common and most straightforward of those. So, very common way to express that analysis. It is an upper bound on the running time. So, it's basically saying, okay, it's going to grow no faster than this. When we say big O of n squared, then that's saying the program running time is going to grow by no more than n squared as it increases. Notice that it does ignore constants and lower order terms. So we don't have big O of 2n, we have big O of n. If it takes twice n to run, that's fine. 6n squared plus 10n plus 1500 is just big O of n squared. N squared minus 5 is also n squared. What we care about here when we're expressing things in this way is growth. So the first thing we're going to do is to just figure out what input characteristic or characteristics should affect the running time. So what is it that is doing that? Is it the size of the graph and the number of nodes? Is it the size of the graph in terms of number of nodes and in terms of number of edges? That's going to depend on your representation for that graph. We might also have cases where it's just the size of a number, as we mentioned before with factorial. Once we know what that input characteristic is, we're going to calculate the number of times that the relevant operations or steps are happening based on the input characteristic. In doing that, we're going to especially consider things like loops, where we need to consider the condition computation cost, which can sometimes be quite expensive. And we need to consider nesting. We're going to multiply out from our most inner loop to our outer loop as appropriate, though we need to consider carefully, because sometimes we can have a nested loop and it's still just big O of n. Have to pay attention to the logic in the loop. We also, if we have recursion, need to consider what's the pattern of recursion. So if the recursion is just a basic linear recursion, then we may just have a big O of n kind of thing. Or if it's a recursion that is traversing a tree, we're going to end up with basically visiting every node of that tree once. So that's big O of n, where n is the number of nodes in the tree. On the other hand, if we're computing Fibonacci numbers, it's a much larger value in terms of the size of the index of the Fibonacci number. So we need to look at the behavior of that. And of course, if else's, we're going to take the max of whichever the if or the else. And of course, we also have to consider the condition there as well. We're going to go through the code, do this calculation, which is a bit of a science and a bit of an art. And then we're going to see what we came up with, drop the constant factors, drop the lower order terms, and we have the big O. Now, once we have that, we may want to deal with the real world. Theory is great, but experiments and actual data are also valuable. So what we often want to do is to look at actual data on running times to see whether our theoretical running time does in fact make sense for the actual program. So when we run the program, does it match what we calculated? We need to know how to compare the theoretical running time with the actual numbers that we got. If our theory says big O of n, then if I double the input characteristic size, I should double the running time. If I try to compute a factorial for double the size of a number, I should double the running time because it's big O of n. And so I can look at the running times and see if that's the behavior that I'm getting. Now, this is approximately. Remember, we've ignored lower order terms. We've ignored any overhead. In squared, if I double, I'm going to be 4 times the running time, approximately. Into the fourth, if I double it, I'm going to have 16 times. So that's the idea, is I can look at these running times and look at the relationship. What I'm doing with the input characteristic is the running time changing in a way that makes sense for my analysis. Let's look at a couple of these. Suppose I have an algorithm that I think is big O of n, and I have some different input sizes, and I'm doubling them. Then I want to see what happens with the runtime. And in this case, I'm seeing that I go from 0.3 to 0.5. So I can actually just divide the running times and see what the factor is. And that's 1.67, which is somewhat close to 2. The next pair, the 0.09 to 0.05, is closer to 2. And the next pair is actually just a little bit over. Now remember, running times are not perfect. We have overhead, we have other things going on. But while none of these are exactly 2, they are relatively close to it, especially when we consider that we have very small runtimes to start with. And one of the realities is there is overhead involved in starting a program, in doing output, if there's output that happens only once, these kinds of things that will impact more when we have very small values versus very large ones. All in all, we can say this analysis is probably accurate. Let's look at another one. This one's, we think it's n cubed. So as we analyzed it, that's what we came up with. With our input sizes, we started with 0.04 for 1,000. We doubled that and got 0.3. Now, for into the third, we expect things to go up by a factor of 8 if I double them. Now, if I am multiplying them by 10, I would expect it to go up by a factor of 1,000. Whatever I'm changing in the input size, then I want to see a corresponding change in the running time. So here, 0.3 divided by 0.04, 7.5. So that's not quite 8, but close. 2.39 divided by 0.3 for the next pair is quite a bit closer to 8. And actually, in this case, 19.12 divided by 2.39 is exactly 8. 2 to the third is 8. These factors absolutely make sense. And we would actually expect that the smaller the input, the more overhead might be reducing the factor. So these make a lot of sense. We can assume that our analysis is almost certainly, in this case, accurate. So let's look at a third example. In this one, we think that it's into the fourth. We're going to use some smaller inputs because we're concerned about growth happening too quickly. We have 0.79 divided by 0.04 is 19.75. Now that's a bit of a red flag here because we doubled the input. 2 to the fourth is 16. And 19.75 is quite a bit larger than 16. Not hugely so, but somewhat. And this is at the small end where we expect to see more overhead, reducing that factor, not increasing it. But let's look at the next one. 23.65 divided by 0.79 is 29.94. That's nearly 30. That seems like our analysis might be off. So So let's look at the last one, and we have 758.32 divided by 23.65. Notice this is seconds. So when we're talking about higher order numbers, this can take a while. This evidence is sort of leading me to believe that my analysis is off and that maybe this is an into the fifth instead of an into the fourth. Clearly off. So the analysis is almost certainly wrong. It's great to look at tables, but let's actually look at some code and the timings that we've produced for it. Okay, so we're going to look at a couple of examples here. The first one is just a short program with a simple big O of end loop. And so I'm going to read the value that my input characteristic, which I'm using the size of that. We're just doing a simple counting loop. So we read that from the command line, then we're going to count and print the result. And what we're going to do for timing is to use a very simple Linux/Unix utility called time. So let's first build our program. And then we're going to use this time. And let's see what happens if I just do 10. Prints 10, which is good. We expect that. And we're seeing 0.005 seconds of runtime. Let's see what happens with 100. Now that was actually less. Did you see that? That was just 0.003. Just looking at this, by the way, real time we generally don't care about. It doesn't matter unless we're doing something like parallel processing, where we're interested in how much time is passing. In many cases, we're sharing the computer with other things. So when we're doing these kinds of analysis, what we really care about is generally going to be the sum of the user time, which is the amount of time the CPU executed user code, and system time, the amount of time the CPU executed system code. So that's what's interesting to us. This is lower. The likely reason for that is that we just created this. There was some extra work loading it in. Since the program had already run, it probably didn't require as much overhead for the program to get loaded and running. That wouldn't matter that much, except these are very small values. So if we run the 10 again, we're going to see 1.03, 100 again, 0.001, 0.001. This is all very confusing. But let's keep going up. 1,000, we're still not getting much size. 10,000, we're still not seeing much. 100,000, this is crazy. 1,000,000. The reality is, computers count really fast. We're not seeing growth here because this is just too small. And quite frankly, I'm running this on a very powerful little gaming laptop. It goes fast. Let's go ahead and raise it one more. That actually does 0.008. Let's see what happens if I double that. See if we're high enough that we're beginning to see reasonable behaviors. And in fact, we do see a reasonable behavior at this point. We actually went from 0.008 to 0.016 if we look at the pair, which is exactly what we would expect doubling. And the next step, we don't get a complete double, but it's close. So we're starting to see that linear is probably a reasonable analysis here. However, it's important to recognize that there's a lot of overhead. If we're doing something that's very fast, then we may see some very tiny times, and there's some overhead involved in just getting the program up and running, as well as in printing the output. Input and output are very expensive compared to running things within the CPU, so that can dominate our time. Let's actually take the for loop out entirely. So I'm going to actually just comment that out. And then I'm going to recompile, and rerun. And we can see that with no loop at all, it still takes a little time to run. And of course, this can vary from one time to another. So when you're doing this, it's a good idea to do multiple trials. Look at the average of 3 runs to make sure that you're getting real data, and make sure your data is big enough that it's not being overwhelmed by overhead. Let's take a quick look at a little bit higher order problem. So I have here a little program that is into the 6th. So we're still taking an in value off the command line. And then I've got 3 nested loops here, each of which runs 2 num times num. So that would be an n squared loop. So this inner one, this addition is being done n squared times. Then we have to multiply that. Each of those is being done n squared times. And then we need to multiply that times this one. So into the 6th. Let's compile this one and see what kind of behaviors we get. We definitely don't want to run it with these kinds of values. So let's just go 10. And we'll notice that at 10, this is still very small. Even though it's 10 to the 6th, still doesn't take that long. But let's see what happens when we double this one. We go from 0.003 to 0.048. Now, let's get our trusty little calculator out here and see what that actually is. Obviously, we can just do it in our heads, but that's 16. Now, that's a little low because I would expect it to be 64. I doubled 2 to the 6th is 64. So we're looking for a change of 64. Didn't get that, but we did get a change that was a fair bit, that's 2 to the 4th. Let's see what happens if I double it again. And here we have to wait. We're going to actually get 2.822. So let's see what that relationship was. 0.48. That's 58.79. So we are getting pretty close to that 64. So we can guess that as it keeps going up, we're going to see that pattern that we expect to be very, very close to reality. Now, we're not going to run the next one since nearly 3 seconds times something like 64 will pass. So I want to show you one more thing, which is to note the whole overhead versus big O. Here I've made a change to the simple loop where I've added an extra little loop that's going a million times. Notice that this does not change the analysis of this program because this inner loop always takes exactly the same amount of time. It is a constant as far as our analysis goes. It is overhead. It does not change the big O. The big O is still big O of n. So now let's compile this one. And let's run it. Now when we run it with 10, we get a total of 0.01 user and 0.001 system for 0.011. Compared to the N6 loops one was quite a bit less than that at 10. So even though it was n to the 6th, it's quite a bit less than our big O of n. But then when we double this changes to 0.02, the n to the 6th problem, was 0.048. And we're going to see that sort of pattern continue. Remember, we were over 2 seconds for the N6 at 40, but here we're only at 0.039. And notice that the growth that we're seeing makes sense. We went from 11 to 20, from 20 to 39. This is very close to what's happening as we're doubling our sizes. We've just added enough overhead into it that these small numbers aren't getting overwhelmed by the overhead of printing and so forth. And we've added overhead that repeats each time through the loop. I hope you found this helpful. Thanks for watching. Hope to see you in the next video.